Okay. Hello. Hello, everyone. Welcome to my talk. Today, I'm going to show you how you can run large eddy simulations in Julia using the Variational Multiscale Method to study the aerodynamics on your airfoils. The package that I'm referring to is segregated VM solver, which implements a linearized and segregated version of the variational multiscale method in Julia, of course. It is a finite element method, and for the implementation, I've used Gridap, which is a finite element library, an excellent finite element library, fully written in Julia. Today, it's able to solve the incompressible flow. It's also solving it in a time-dependent manner over 3D airfoil geometries, and the code is fully parallelized. So together with the other two packages, synthetic eddy method and airfoil GMSH that I've presented last year at the JuliaCon at MIT, I'm trying to build up an ecosystem where we can study efficiently airfoils in Julia. Here I'm going to show you how you can use the APIs of this package, which is thought and designed to be used not only by expert CFD users. So the user needs, for example, here to supply just the initial time, the time step, and the final time. And then all these parameters are just the structures with keywords. So actually, most of the parameters are set to some default values, and an expert user may want to modify them. So for example, when calling the solver parameters, here an expert user may want to modify the Krylov solver or the preconditioner linked to the velocity system, or for example to the pressure system. Then the user need to supply also the Reynolds at which we want to solve the airfoils. And then the mesh file can be created, for example, using airfoil GMSH, which is the package that I've mentioned before. And then the code is parallelized, so it can be run on clusters, and we need to supply also the number of cores that we want to use. Then in the stabilized problem structures, the variational multiscale method is actually invoked. In fact, here we are constructing our stabilized problem. So the user can choose to use the variational multiscale method, or also the streamline upwind Petrov-Galerkin, which is also implemented. We can use first order elements, second order elements, or even higher order elements. For the user may also want to specify which kind of method he wants to use for compute the stabilization coefficients. So is embedded a tensor formulation, a scalar formulation, and we can activate or not a skew-symmetric formulation, which is going to influence the convective term in the momentum equation. Then we create our simulation case. In this case, we want to solve an airfoil, and here are embedded all the boundary conditions for this specific case. In the package, there are also embedded other cases like the Taylor-Green vortices, the cavity flow, and the cylinder. And then we just can solve our case. If you want, you may also create easily a new case, which here using these simple APIs, which in this case we are creating something that I called box, and then you just have to code your boundary conditions associated to the tags of your new types, and of course supply a compatible mesh. While solving large eddy simulations, usually we produce tons and tons of data that we have to manage somehow. So that's why the package comes also with a series of post-processing tools, which are focused to get span averaged and time averaged. So in the end, you can obtain relatively nice plots of pressure distribution and skin friction over your airfoil. Here on the right, you can see a comparison between the pressure distribution over the SD7003 airfoil. The black line is the one that we are able to obtain through this package, which is implementing a modified version of the variational multiscale method, while the red one is a results that have already been published by other authors, and which is using the variational multiscale a method coming also from the variational multiscale family. So, which are the next step? It will be cool, and it's cool to expand it, this method, with an adjoint formulation, so we can go for some shape of the optimization. Here, the user does not have to supply a mesh anymore, but a parameterization. In this case, I am supplying a parameterization based on CSTs, so class shape transformation. In this way, I'm sure that I'm obtaining always airfoil-like shapes in my optimization process. And then it has to be also coded in optimization functions. In this case, we want to obtain an airfoil with a CL of 0.35. These optimization functions is the function that we want to be minimized. So through an optimization loop, where we are going to compute the gradients of the objective function with respect of our geometrical parameters that we have supplied to parameterize and create our airfoil, we can minimize our objective function. And here in this part, I'm leveraging the NL Optim package for the minimization. The APIs of the adjoint are still not final, not still user-friendly, and I'm still working on that to make it more accessible for everybody. But this is first results that I've obtained so far. So you may see that the airfoil is changing its shapes and converging towards the desired CL, and yeah, that's it. Feel free to try them, to try the packages, and let me know everything. That's it. Thank you. Questions?
Congratulations for a very nice presentation. I do wonder, in your view, what is now required to do this in 3 dimensions instead of only in 2 dimensions?
Because this is an LES, so I need the 3 dimension also to get the correct vorticity. Especially, I'm focused on low Reynolds airfoils, and they develop in special conditions of low turbulence, particular structures, which is called the laminar separation bubble, and capture correctly the turbulence and especially the 3D vorticity. It's crucial for having accurate results. So in 2D results, we may not, is not like runs, so it's an LES, so I need to go 3D.
But having all the code and experience that you have built up thus far, what is in your view missing to go to 3D simulations?
To go to 2D?
To go to 3D?
I'm already 3D.
Ah.
Yeah.
I didn't see that.
Sorry, like this animation is on a DU89 airfoil at 500,000 Reynolds and I think 1 degree angle of attack. The contours are of Z velocity, so you may see the flow in the rear part, the touching, for example. So I'm in 3D, yes.
Thank you very much.
Yeah, thanks for the question.
Yeah, thanks very much for the nice presentation. Which is the key bottleneck on this type of simulations?
Sorry, may you repeat?
Which is the key bottleneck
of
the key bottleneck of your simulations?
I would say that at the moment is the resolution part. So when I'm actually solving the system, now we are calling PETSc, and I am recomputing the preconditioner of the main solver every 20 time step. And this is also a choice can be made by a more expert user. If we want to make the simulation faster, can ask to recompute the heavy preconditioner maybe every 40 or 50 time steps. Or if you have enough resources, you can reduce this time. So at the moment, and I'm also I've seen that at some point the code, especially when computing preconditioner, is allocating a lot. So yeah, I would say that's it.
Yeah, okay, thank you.
Thank you.
I had a follow-up question to that. But, is there a reason why you're using PETSc as opposed to like ordinary diffeq?
For solve my final system,
Yeah.
yes, because it's sparse and distributed, and is one of the option available. I'm considering other options.
Okay.
You were suggesting
Yeah,
what?
ordinary diffq.jl works with sparsity already, and
As is
you
also
can
distributed for work for clusters.
you can customize your linear solver to use
Okay.
a sparse linear solver. Yeah.
And also a suite of preconditioner that works.
Yep.
Okay, okay.
Yeah.
I will migrate to that and see
yeah,
if
we can talk
performance
about that after.
Hi, thanks for the presentation. Maybe I didn't get this very well, but on your optimization problem,
Yes.
the way you compute your adjoin, so are you doing this with AD, I guess?
Is a continuous adjoint.
Yeah.
Now I have hard coded, so I've coded explicitly the formulation, and the next step is to obtain the AD and have a comparison if the two match. So I also have a kind of comparison to see if I'm coding correctly the.
So you're
automatic
doing like a
differentiation.
finite difference currently, where you increase a
Sorry?
bit. What's the way that you compute the derivative right now with this continuous adjoin?
Yes.
Can you maybe go to that slide if you had that implemented?
Well, yeah, I haven't read it down here. I don't. Yeah, it's in my loop.
Okay. Okay. Well, I will ask you about this
Okay.
later, maybe. Yeah.
Okay, thanks.
Thank you very much.